And then you said 11. 11 says to go down 1 and right 3, but it's the absolute value. So down 1, right 3. If I'm absolute value, the right is going to be minus 3 inside the absolute value signs. The down 1 is going to be minus 1 outside. So again, right 3, 1, 2, 3, down 1. What's the domain? Negative, infinity, infinity. What's the range? There you go. All right, y'all ready to do dilations? Yes, but you're going to have to actually use it to find the points for which it changes. We'll do reflections first, then we'll do. I'm going to try to get through this as quickly as possible so you can work on your. Yeah. We can reflect, and remember we talked about all of these yesterday, but we're going to go in a little more depth here today. So we can reflect over the x-axis or the y-axis. If I reflect over x, this means I negate or change the sign of y. And in the form in function notation, reflecting over x is when you put a negative out in front of the entire equation. Okay? Think about your your quadratics. Whenever we did them, we said if that a was negative, it was upside down. That's why it was upside down. It was reflecting over the x-axis. I can also reflect over y. And if I do that, then what do you think I negate? The x. And for reflecting over the y-axis, and this would just be the vertical axis was a mirror and it was the same on either side. So some things, if they're already symmetric about the y-axis, you're not going to reflect them over y. But to do this, every x gets a negative in front of it in the equation itself. Okay? So the difference there and what that looks like. So if I gave you the, I'll give you, y'all done? If I gave you the equation, what does that look like? It's just reflected over the x-axis, right? So the parent graph, 0, 0, 1, 1, negative 1, 1, looks like this. But to do the reflection, every y is negated, right? One, 1 becomes 1, negative 1, 0, 0 stays 0, 0, negative 1, 1 becomes negative 1, negative 1. You see how the y values there change, but the x's stayed the same? There's the reflection. Reflections are pretty easy. No, that's good. That's all I'm gonna do because we're gonna jump into dilations. Oh, no, I appreciate y'all's enthusiasm. Thank you. Thank you. Oh, I just found my packet. Um, I'm looking for Milo. What color did I make your sheet? Green? All right, let's move into dilations because that's what I really wanted to get to today. What? Because these don't really go across Y. They are for right now. For right now. Tell me this. what would the equation look like for a quadratic function that has been shifted up 5 units, down, nope, right 2 units, and reflected over x? Give me an equation. Take just a minute. Take just a minute. No. Up. Well, you can't hurt yourself. I asked for that one. It's a strawberry. Well, I don't know. No, you're sick. Not yet. All right, so the quadratic is the squared, right?
I do, because it's wrong.
All right, I've got x. The right 2 is going to be minus 2 squared. Up 5 is plus 5. And then to reflect over x, does the x get negated or the in front get negated? Where do I put the negative? In front. Easy peasy? Thank you.
Life gives you lemons, eat them.
All right, here we go. Y'all ready for the shrinks and stretches? Get out of my... Dilations.
It's just the 1/2 thing, and it's like wider.
I'm fixing to tell you all about it. Let's talk about vertical dilations first. Vertical shrinks and stretches. This is whenever I have a number that's out in front, whether, like what we've been doing has been, well, I'll just say a times f of x. As opposed to hook just to the x, okay? So this is what it seems to be. So if it's bigger than 1, and we're going to say absolute value because the negative only has to do with reflections. So if a is bigger than 1, it's a vertical stretch. Now, if it's a vertical stretch, does that mean I'm getting skinnier or wider? Skinnier, right? Because if I stretch out that vertical axis, my graph is shrinking in and getting skinnier. And if a is less than 1, so I'm talking about fractions that are small, that's a vertical shrink, which means, think about like an Oreo that you're smushing and the cream comes out the middle, right? Your graph's getting wider and wider and wider. So I'm like, what is this? What? I give up. Do you ever get kicked out of class, Logan?
Kick me out. Leave.
No.
Kick him out.
But it's not, I can't explain it like that because it's true for any and everything. It's not always slow. Right now it is. But you have to understand that it could be.
Quadratics and absolute value of dilations, right?
Yeah, but if I had this, it's not slow. So I have to teach you how, right?
Yeah, but we're not doing that.
But you might have some funky on your project.
I can't load my project.
All right. Vertical stretch. So here's the question. The question is, how do I find the points whenever I have this A value? So this is where your cheat sheet's really going to come in. Some of my pre-cal kids, I did it on red last year. They still have their red sheet and they're still using it in class. But, well, okay. No. if it's a vertical stretch or shrink, right, that means I take the point that was there, and every point that was there, look at your vertical, a times f of x, the x stays the same, and I multiply every y by a. Straight out of luck. Straight out of luck. Straight out of luck. Straight out of luck. Yeah, straight out of luck.
I ain't gonna lie, I already lost. I think I might still have it. I just don't remember.
Thank you guys. Who told you that? Some things you'll be able to use it on and others you won't. It's a good idea to hang on to it though. All right. Let's say, for example, go sit down. What is this? Vertical or horizontal? Vertical, it's vertical. A vertical shrink, so it should be wider, right? And my A here is 1/2, yes? So here's what I'm going to do. I'm going to take every point. Okay, yes, but that's what Logan was saying. But all your parents don't have a slope that way to get to the next point. See what I'm saying?
Yeah, but we're not doing any of that now.
Here's my parent.
So what's stopping me from going from my vertex to going up one over two?
Because if I ask you to describe this, or
I went up one over two. Can't you just say that's a horizontal stretch?
yeah, but it's not a horizontal stretch. You have to give the factor by which it's being stretched or shrunk. Okay.
Yeah.
So if you say it's horizontal, no, it's not a horizontal. All right, let's stick with vertical. This is a vertical shrink or compression of 1/2. So that means every point that was on the parent, I'm going to take it, I'm going to keep x the same, and I'm going to multiply every y by 1/2. I'm going to cut every y in half, okay? Right now I've only got you doing 3 points, but here in just a bit we're going to do more than just 3 points, and so your slope won't serve you anymore. Does that make sense? Because 2, 4 is on this graph, right? This is the parent graph. So to find out where these points are, here's what I have to do. I keep x the same. This is coming right off of your sheet. I keep x the same, and I multiply every y by that a value. So 0, 0 becomes, obviously still 0, 0, right? 1, 1 becomes what? 1, 1/2. 2, 4 becomes 2, 2. 1/2 times. You multiply the y value by that factor. Okay? So now I got 0, 0, 1, 1/2, and 2, 2. So, yes, do you see why? Yes. So every point on the parent gets impacted by this vertical factor. Okay? Whether it's shrink or stretch, I take that number and I multiply every y by it. Does that make sense? Are y'all okay? Vertical or horizontal? Shrink or stretch? We haven't gotten to it yet, but I'm guessing, yeah. Vertical, it was a trick. Stretch of 3. Because it's up. No, stay up. All right. Vertical stretch of 3. Graph the stretched function using at least 5 points. At least 5. 5
is the minimum. We're doing value.
Well, yeah, because I'm going from the parent.
Unless you have a birthday somewhere else.
So whenever we're transforming, we always do stretches and shrinks first, and then we do slides. So we'll always transform. We'll always stretch or shrink the parent. Then we'll do any reflections. And then the last thing we'll do are any slides, left, right, up, or down.
Yeah, like why didn't you do one
I just didn't graph the parent. Is that what you're saying? This is the parent. And then the blue one there is the one that's vertically stretched. Does that make sense?
I mean, somewhat.
Logan. And Charlie. Yeah, sure. I probably answered it while you were talking to Logan about Bolt and Leo. Zero, zero. 1, 1. If you plug in 2, what do you get? You plug in 2 to this equation. 4. So 2, 4 is here. So this is one side. And then I can just reflect. Square your x. Yeah. That's right. Yep. Make sure you write this down somewhere. We're going to get into combinations soon. Just a minute. Yeah, yep. Mm-hmm. All right. Yes. Yep. Mm-hmm. So remember it's xy becomes xa times y. Your a is 3, so every y gets multiplied by 3. These are tough. These get tough. Do y'all not remember these? Last semester said they remembered these from last year.
No.
Hmm. I'm listening. You need to do the shrink stretch first. No, I'll probably make you show the series of transformations. Until you get used to them. Okay, let's do horizontal and look at the difference. This time, and this is where it gets tricky because everything is opposite, okay? So, this time, I'm multiplying just the x by something. These are a little bit harder to see, but remember, horizontal and vertical can be the same thing. A vertical stretch is the same thing as a horizontal shrink and vice versa. But so this is before the other one was in front, right? So if I had f of x equals 1/2 times the absolute value of x, then hooked to it, if I had, and I know in this case it's the same thing, but it's not always. See how it's hooked with x and included in any grouping symbols? That's the difference in vertical as opposed to horizontal. If it was a quadratic, that's vertical. That's horizontal. We mostly focus on vertical, but horizontals come up. All right, so A is still my shrink or stretch factor, but it's the opposite of what you think it is. So if A, again, absolute value, right, is bigger than 1, and here's where it's tricky, then it's a horizontal shrink or compression, same thing. But if A is less than 1, then it's a horizontal stretch. You know how I was writing vertical stretch of whatever, horizontal or vertical shrink of the, like of 3, where Logan wanted to say by 3, but it was of 3. This time, the factor that we say it's a horizontal compression or a horizontal shrink of, and then I have to flip that A over. Okay, so for example, if I had this is horizontal because it's hooked to the x, yes? And it's less than 1. So this is a horizontal stretch of, what do you think it's of? What's the stretch factor? I've got the 1 over A just means flip it, of 2. Tell me what's going on with that one.
That is.
This is reflect. See how I flipped it there? It's a 3 here, but the factor is 1/3. Okay? And here's why that's important also, because if you look at your little cheat sheet, right, For horizontals, I take xy, and what I have to do, it says x over a and keep y the same. That is the same thing as saying 1 over a times x and keep y. This is just the flip of a. So every x would get multiplied by 2, or every x would get multiplied by 1/3. Okay? So we need to get used to seeing the flip of that. So let me show you a couple examples. And let's see what happens. Horizontal is kind of difficult. You ready? Here we go. I'm almost done, I promise. Tell me what's going on. Horizontal. Is it a shrink or a stretch? Stretch. Horizontal stretch of, what's the factor? 2. Horizontal is always opposite. Always. Well, right now, you can use your little green sheet and look. But if it's done only to x, this is horizontal. If it looked this way, that's vertical. You're looking for it to be in parentheses or in some type of grouping with the x to be horizontal. Vertical is what it is. Horizontal is opposite. All right, so now what this says is this says take every point on the parent. Every x gets multiplied by 2, and every y stays the same. Even though this says a half, it gets multiplied by the flip of that. So now, think about the parent. On the parent, I have 0, 0, 1, 1, and 2, 4, right? Because it's a quadratic. So 0, 0 becomes still 0, 0. 1, 1 is going to become what? 2, 1. We're using the flip of the 1/2. And then 2, 4 becomes 4, 4. You use the flip. And that's on your little cheat sheet. That's one of your little cheat codes over here on the side. Yes. So this graph would look this way. 0, 0. 2, 1. And 4, 4. Again with the reflection. Does that look like a horizontal stretch? If you could take that horizontal axis and stretch it out, is that what looks like happened? Yes, because it's wide. What's the parent function? What is it? What's the parent? Absolute value. Thank you. Are y'all just scared to answer? We've only done two right here. We've done the same two. If it's a sharp point, it's absolute value. If it's a nice curve, it's quadratic. Yeah. Do you see this as a vertical or a horizontal dilation? Vertical, somebody said vertical, okay. Why? What's it look like's happened? It's getting skinnier, right? Okay, so I can describe this one of two ways. We're gonna write this equation. I could say if it got skinnier that it's a vertical stretch, right? Or I could say that it's a horizontal shrink. So here's what I want to do. I'm going to look at this point. What's being changed is the first point, the X or the Y? The Y. So I think that I will describe this vertically because the Y is being changed. Does that make sense? If the X had been changed, I'd describe it horizontally because that's the horizontal axis. But since this, and in fact, it looks like 1, 1 became 1, 3. Would you agree with that? Yes. If 1, 1 became 1, 3, and I've already said it's a vertical stretch, then it's a vertical stretch of what? 3, because I multiplied the Y by 3. Does that make sense? Write an equation of an absolute value with a vertical stretch of 3. Yes. Yes, but what I would do is I'd look for a point that either has a 1 for the X or a 1 for the Y. So then I'd know which one's easier to write the equation for. In this case, the Y changed, X stayed same, so it's easier just to do it as vertical. Okay, here's what I want you to do. Got a little bit more tonight, but you got some time to work now. Tonight, 3:36. But listen, all these are single transformations with the exception of some negatives in there. Now tomorrow, well, dang it. 3:36.